Hello everyone, this is John. Welcome to an episode of AP Chemistry. Today we're going to talk about the galvanic cell. The term galvanic cell might sound intimidating, but don't be scared, because it's actually a very simple concept which you will understand after watching this video. The galvanic cell is also called the voltaic cell in some textbooks. I'm just gonna call it galvanic cell in this video, but they really mean the same thing. If you have never heard of the term galvanic or voltaic, it's okay. You have probably heard of the term volt, which has to do with electricity. So does the galvanic cell. A galvanic cell is an electrochemical cell that derives electrical energy from spontaneous redox reactions taking place within the cell. How it works is, when the switch is closed, the electrons flow from one end to the other, almost like a circuit. Except the galvanic cell is actually a device in a circuit that keeps the electronic potential, or voltage, constant, just like battery. In fact, the galvanic cell is the concept behind how batteries work. Let me remind you of the redox reaction. A reduction is the gaining of electrons, and the oxidation is the losing of electrons. You are going to need to get that straight before you go any further. On the AP exam, you're often given something like this. This is an example of a galvanic cell, so let's break it down. Suppose we're using the redox reaction from the previous slide. So we have solid zinc and copper 2 plus aqueous solution, and they're going to react and produce zinc 2 plus aqueous solution, zinc 2 plus aqueous solution, and guess what? Solid copper. So that overall reaction can be broken down into two separate steps. So the first one is, so the solid zinc is going to be oxidized in this reaction. It's going to become zinc 2 plus, and it's going to produce 2 electrons. And copper 2 plus aqueous solution, on the other hand, is going to be reduced. It's going to take the 2 electrons and become solid copper. So now let's take a look at how the galvanic cell is going to look like in this reaction. So let's draw a metal bar, which is called electrode over here, and another electrode over here. This electrode is made of zinc, and this electrode is made of copper. Both of these electrodes are synced in a beaker. There's a beaker that contains aqueous solutions separately. And in this beaker, we have copper 2 plus ions and maybe something else. And here we have zinc 2 plus ions. So in order for this reaction to happen, we need wire at the top to transfer the electrons. At the zinc side of the electrode, zinc 2 plus ions is jumping off of the zinc metal bar, and at the same time is giving off electrons, which is being transferred by the wire. At the copper electrode, copper 2 plus ions is receiving the 2 electrons and is becoming solid copper. The electrons are being transferred from zinc to copper. It is moving in this direction. As you can tell, the copper side is being reduced by definition. This is where the reduction occurs. It's receiving electrons, while the zinc side is where the oxidation occurs, as is releasing electrons. We call the electrode where the oxidation occurs as the anode, and where the reduction occurs as the cathode. On the AP exam, it is extremely important to remember what type of half reaction happens at which electrode in the cell. They almost always have a few questions asking you to name the cathode and anode. There are many creative ways to memorize this. Your teacher might tell you anode and oxidation both start with a vowel. I came in with another way to remember this. Remember I told you a few minutes ago that a galvanic cell is just a battery. Think of a battery in baseball. The pitcher throws pitches to the catcher, and the catcher receives the baseball. In this analogy, the baseballs are electrons, and the catcher is the cathode that receives electrons. Since cathode and catcher both start with CAT, they always go together. So next time you see an electrode that is receiving or quote-unquote catching electrons, you know that electrode is the cathode. And of course, the anode is the other end that is giving off electrons. Now we have gotten this far into the topic. You might look at this cell and say, I think we have all we need now. But imagine with just what we have right now, what would happen? If the zinc 2 plus ions just keeps jumping into the aqueous solution, the solution will become extremely positive. And if the copper 2 plus ions just keeps jumping onto the metal, then that solution will be extremely negative. So what do we need to have in between to keep the two solutions neutral so that the reaction can actually complete? That's right, we still need the salt bridge. You might ask me, why is the salt bridge even there? Well, let's go back to the baseball illustration. After the catcher receives the ball, he has to throw the baseball back to the pitcher, or the pitcher will simply run out of baseballs after just a few pitches. For our purpose, there has to be a device that balances out charges for the circuit to complete. Otherwise, the galvanic cell simply would not work. And that device is the salt bridge. What's in the salt bridge is usually an aqueous solution. Let's just say the salt bridge is made of nitrate ions and sodium ions. In the salt bridge, the anion always goes to the anode, and the cation always goes to the cathode. In this case, the nitrate ions goes into the zinc 2 plus aqueous solution to balance out the charges, and the sodium ion goes into the cathode to compensate the loss of copper 2 plus ions. The trick to remember this is that negative charges always moves in one direction. If the electrons move from zinc to copper, then the anion certainly moves from copper to zinc to complete the circuit. Now let's look at the real problem on the AP exam. We are given a galvanic cell which electrodes are made of copper and tin, respectively. We also know that the copper electrode increases in mass and tin electrodes decreases in mass. So what can we know from that? If the mass of the copper is increasing, that means the copper ions are jumping onto the metal bar, while the tin ions are jumping off of the metal bar, as you can see here. If that's the case, then the electrons are transferring from the tin side to the copper side of the electrode. So the copper is the receiving end of the electrode, therefore the cathode, while the tin is the giving end of the electrons, therefore it is the anode. Now, I always encourage you to write down which side is the anode and which side is the cathode. That way, it's very clear which electrode is receiving electrons and which electrode is giving off electrons. That will help you to do further questions. Now let's answer the two questions we have here. Number 1, which electrode is being oxidized? By definition, the anode is the side that is being oxidized. And remember, anode and oxidized both starts with a vowel. Now let's look at the second question. Where's the mass of tin going? Actually, we already answered that question on the graph. As the anode is releasing electrons, the tin 2 plus ions are jumping into the aqueous solution. So the mass of the tin is actually going into the aqueous solution. After watching this video, I hope you understood what a galvanic cell is. To review the context, ask yourself what is an electrode? What is the difference between a cathode and anode? What is the purpose of a salt bridge? In which direction does electrons flow? If you can answer all of those questions, you are good to go. Thanks for watching, and see you next time.